Hello everyone. So in this video we'll take the electric field due to the infinite sheet of charge. So we are going to find the expression of electric field intensity due to infinite sheet of charge. In the previous video I have told you about the electric field intensity due to the infinite line charge distribution and due to the circular charge ring. Okay, so now here we are going to look the इनफाइनाइट शीट ऑफ चार्ज. ओके, तो अब देखिए अब यहाँ पास सो फॉर दिस विल कंसिडर एन इनफाइनाइट शीट ऑफ चार्ज हैविंग यूनिफॉर्म चार्ज डेंसिटी इज रो एस एंड द यूनिट वी नो इज गिवन एज द कूलम पर स्क्वायर मीटर, राइट. एंड this infinite sheet of charge is placed on the xy plane, you can say. Okay, and now take this this is the point P where the electric field intensity has to be find out. Okay, and this is the I have taken a differential amount of the surface which contain the differential amount of the charge is dq, right. And we can say this is the r is the distance of this point P from the differential surface ds, right. So I can say that the differential charge dq, so dq will be given as the rho s into ds, rho s into ds, and ds is here we can say the normal direction to this differential surface is what? That is the z directions, right. Hence ds normal to z direction we can define as the ds will be given as the r dr d phi, r dr and d phi we can say. So we can say the electric field differential electric field intensity term we can write this will be given as the dq upon this is given the 4 pi epsilon naught, this is the r square and this is given as the ar, and further we can write it this is given as the rho s and ds we can write this is given as the r dr d phi divided by 4 pi epsilon naught, this is the r square and this is the ar we can say. So basically we can say this r having two components, जैसे आप देख सकते हैं यहाँ पर मैंने इसको और एलिब्रेट किया हुआ है. तो this r having the two components, basically we can say that one is the radial component r along the ar direction, so this is the minus ar direction is reversed, and this is the you can say the component along the z axis, so this is given as the z we can say. Okay, so we can take the this component z, so we can define this vector r, we can say this vector r will be defined as how a minus r ar we can write plus this is given as the z, right. And further we can find the magnitude of this, so we can write this is given as the r square plus z square, right. And also we can find the unit vector which is given as the vector r divided by of its mod r, so we can write this is given as the minus r ar, this is given the z divided by its magnitude which is the r square plus z of square we can say. Okay, so in this fashion we can find the unit vector. So if we put these values in the expression of differential electric field intensity, so we can write this is given as the rho s, we can write the rho s r dr d phi divided by 4 pi epsilon naught, this is given the r square plus z square and this is the under root whole square into the unit vector ar, so we'll put this is the minus r ar plus z divided by magnitude of r square plus z of square. Okay, so now to find this whole electric field intensity for this entire sheet of charge, so we have to disintegrate this with respect to the dr and the d phi. And one more thing I can say here that there is a symmetricity about the z axis from the all the direction, you can say from the all the radial directions. So we can say the radial component, so we can say the radial component from the all direction is going to be cancel each other, so there will be the no radial component will be available in the electric field intensity expression, right? So the expression we have written, or we can write here, this will be given as this phi. Now phi will varies from 0 to 2 pi, and r is varies from 0 to infinity. Okay, and we will differentiate the expression of differential electric field intensity, or we can say this is given as the, so phi varies from 0 to 2 pi, and this r is varies from 0 to infinity. And if we put the values of dE, which is given as the rho s r dr d phi divided by 4 pi epsilon naught, this is given the r square z square to the power 3 by 2, and this is the z az. As I told you, we will not get the any radial component, so ar will be eliminated. Either if we'll take this ar here in the expression, and if we'll find for the integration, then ultimately in the solution that the component will be cancelled out. Okay, so always we remember that all the radial component will be eliminated, or you can say that will be cancelled to each other. So further, now we have to for the solution of this integration, now we will use some substitution method. So we'll put here the r square plus z square equal to u square, and hence we can write this is the 2r dr will be equal to 2u du. And further we can say for the limit, so when r is equal to 0, so we can say the u will be equal to what? It will be equal to z. And also we can say when the r is equal to infinity, so we can say the u will be equal to what? It is also equal to the infinity. Okay, so now here further we can take the electric field equation. So this is given as the, so we know the phi is varies from 0 to 2 pi, and here the u is not going to vary from z to infinity. Okay, now if we put the value, so this is given as the rho s, and in the r dr we can put the u du. So we can put the u du is here. Okay, and we can say this is given as the 4 pi epsilon, and this r square plus z square we can put the u square. So we can put this is the u square 3 by 2, and this is given as the d phi z az is there. Okay, and so further if we'll take the integration for this, so we can put this phi is varies from 0 to 2 pi, and u varies from z to infinity. Then we can say this become what? Rho s upon 4 pi epsilon naught, and this become 1 upon u square. So we can say this become the du u square we can say, and this become the d phi, and this the z and az will be there. Okay, so now you can say that if we'll integrate, I can take this one constant. So this is the rho s upon 4 pi epsilon naught, and this is given the z az. I can write it as a constant, so I can take the integration where is 0 to 2 pi. You can say this is for the d phi, and also we can say u varies from 0 to infinity. So this is given the 1 by u square, this is du. So when you will solve this one, so ultimately we'll get the expression that will be, I can write it for rho s upon 4 pi epsilon naught. Okay, so this is given the 4 pi epsilon naught is here, and this become the 2 pi az. Okay, and in the further if I'll solve this one, so I can write it, this electric field intensity expression is become rho s upon 2 epsilon naught az. So this is the final expression for the electric field intensity due to the infinite sheet of charge. Unit will be volt per meter. Okay, so always remember here the Az is the normal component, or you can say the normal to the differential surface element, as we have taken in this case the differential surface element in for the xy plane, so normal to that will be the z direction, so this Az will be normal, and in standard form we can write this electric field intensity expression as rho s upon 2 epsilon naught. This is given as the An. So An is, we can represent as the normal to the sheet, normal to the plane which consists the infinite sheet, right, volt per meter. So this is our standard formula, we can say, for the electric field intensity due to the infinite sheet of charge. Okay, so in the further video I will take some of the numericals and I will tell you clear that how we are going to use this expression for the numerical, so this will going to be clear to you. This is very important, the question have been asked from this expression. Okay, so this is the electric field intensity due to the infinite sheet of charge. Thank you.